Okay.
Sorry,
Maybe
great.
that's another problem.
And that was written by Miriam Backens.
Oh, that's right.
Thank you. So yes, my main focus of this talk is going to be the approximate completeness result, or well, yeah, the result that the ZX calculus is complete for the Clifford plus T group on single qubits, which is approximately universal. In the interest of giving a complete overview over completeness result for the calculus, I'm also going to say a few things at the end about the stabilizer completeness result that Vladimir already referred to. But yeah, the main focus is going to be on the single qubit Clifford plus T group. So this is the structure of my talk. I'm first going to give some motivation. I'm then going to spend the main part of the talk talking about single qubits and the Clifford plus T group. Then completeness for stabilizer diagrams, and finally some conclusions. So as we just heard, the ZX calculus is incomplete, and it's not at all obvious how to complete it, even for single qubits. So instead we're going to look at restricting our diagrams, in particular by restricting the phases, because that's where kind of the specific counterexample here comes from. But we can also restrict our diagrams to specific structures, and in fact for the single qubit completeness proof, that's something we're going to have to do, hence why it's single qubits. And yeah, as I said, I've used this term approximately completeness, which may not be very well chosen, to mean that it's complete for an approximately universal set. So, single qubits. The specific approximately universal set we're using here is the single qubit Clifford plus T group. So we have a single qubit Clifford group generated by the phase gate and the Hadamard gate, and additionally we have this T operator, which is the square root of S. And in the ZX calculus, we just represent these as a green pi by 2 phase, this Hadamard node, and a green pi by 4 phase shift. An alternative generating set for the single qubit Clifford plus T group is just using the green pi by 4 phase shift and the red pi by 2, because the green pi by 4 can square to the green pi by 2, and then if we have a green pi by 2 and the red pi by 2, that gives us the Hadamard. And as you can see, each of our generators has exactly one input and one output. So when we say single qubit, what we actually mean is that all our diagrams are line graphs, and all our elements will have exactly one input and one output. And because our generators only have phases that are integer multiples of pi by 4, obviously we will restrict our diagrams in such a way that all phases have to be multiples of pi by 4. In this talk, I'm also going to ignore global phases, which doesn't actually break any incompleteness or completeness result. It's just, yeah, easier to just not have to bother with all those scalar multiples. So because we restricted our diagrams so heavily, our rules also simplify significantly. I'm just quickly going to recap the ones that I will be using in the main part of the talk. So we still have the spider rule, which now takes this very simple form. We have a pi commutation rule, which is pretty much the same as before. Our color change rule has simplified somewhat. And we still have this Euler decomposition of the Hadamard gate. As you can see, the one I've given here is actually slightly different to the one that Vladimir gave. That's because there are 4 equivalent ways of expressing the Hadamard in terms of red and green phase shifts. So we can add minus signs in front of each of these phases, and we can also swap the colors, and that gives us the 4 different representations of the Hadamard. And we've still got the identity rule, which means that if we have a node that has a phase which is an integer multiple of 2 pi, then that's the same as just a single line, which is the identity. Let's first go off on the side on just single qubit Clifford diagrams. So diagrams where all phases are multiples of pi by 2. And it's fairly easy to prove normal form results for those diagrams, because when we ignore global phases, there are only 24 different single qubit Clifford operators. And so one possible normal form for single qubit Clifford diagrams is this. So we can have an arbitrary red phase followed by an arbitrary green one. Arbitrary here in the sense of they still have to be multiples of pi by 2. But within that, they're arbitrary. Or we can have a green pi by 2 followed by a red plus minus pi by 2 followed by some green phase. We can also have a second different Clifford normal form. I'm going to use both of these in the subsequent talk, which is why I'm introducing them both here. So as you can see, the second one's pretty much the first one upside down, except we've now also changed things so that here our red phase has to be an integer multiple of pi, whereas all the cases where the red phase is a multiple of pi by 2 and not pi are kind of contained in the second type of diagram. And in fact, in the talk going forward, anytime I use Roman numerals, they're going to take values in the set 0, 1, and anytime I use Greek letters, Roman letters, Latin letters, anytime I use Greek letters, they're going to be angles that are multiples of pi by 2. So anytime anything has an angle that's a multiple of pi by 4, I'm going to explicitly say that. This is the normal form for single qubit Clifford plus Tia diagrams, which is the core of our proof. This normal form is unique, and because all our rewrite rules are invertible, that means if we have two diagrams which we think may be equal, we reduce them to their normal forms, and then if those normal forms are identical, that means we can just invert one set of rewrite rules, and that gives us a proof within the ZX calculus that the two diagrams are equal. This work is based on a paper by Matsumoto and Amano, where they do pretty much the same thing for quantum circuit diagrams. So this normal form is a bit to unpack. At the bottom, we've got some operator, which I've called U here, and in the future, I'm going to refer to any operators of this form as a U. It's basically an arbitrary Clifford operator with some green pi by 4 sitting on top of it. We've then got some number of copies of things that I've called V, and will in the future also refer to V as V. These are a red pi by 2 followed by a green pi by 4, or a red pi by 2 followed by a green 3 pi by 4 phase. And at the top of the diagram, we have another Clifford operator, but this one's somewhat restricted, so it can only be either an identity, or a red pi by 2, or red pi by 2 followed by green pi by 2. And again, in the future, whenever you see a W somewhere, it's going to be an operator of this form. So the way that this normal form comes about, and the way we're also going to show how to rewrite diagrams into normal form, is basically we're trying to push as much of our phases down to the bottom of the diagram as possible. And we only stop when we can't push things anymore because the rules don't allow us to do that. So we can push arbitrary green phases past a green pi by 4, just by the spider law. And by the pi commutation law, we can push a red pi past a green pi by 4. And similarly, if we have a red pi by 2, we can push arbitrary red phases past that, and we can push a green pi past that as well. So if we push a pi of the other color past an operator, then that will flip the original operator, but that just gives us, we can always split the operator into the original one, and then something that's minus twice the original phase, and then we are left with the original operator again, and we have some more phases to the bottom of it, which is what we want. So because these operators of the form V consist of both a red pi by 2 and some number of copies of green pi by 4, the only things we can push past those are copies of red and green pi. So as an example of how this happens, if we have a general Clifford operator sitting above a green pi by 4, we're now going to use the second normal form for Clifford operators. So this means that this diagram will either look like that or like that, depending on whether we have a red phase that's a multiple of pi or not. As said before, all the Latin letters here are either 0 or 1, and all the Greek letters are multiples of pi by 2. So if we now rewrite this first diagram, trying to push phases through to the bottom, then first thing we can merge the two green nodes by the spider rule, and we can then split them again the other way. So we've pushed the beta through to the bottom. We can now use the pi commutation rule to push our red pi past the green pi by 4, which might flip the phase if this is actually a pi. If it's some other integer multiple, if it's 0 pi, then it's the identity and it doesn't do anything. So now we've got a minus, we might have a minus pi by 4 here, which we don't want. So we're going to split that into pi by 4 and possibly a minus pi by 2. And then we can push that through to the bottom just to simplify the diagram somewhat, and the sign will flip and it will merge with the green node at the bottom. And as we can see, we've managed to push the entire Clifford operator through our pi by 4 in this case, all the way to the bottom, and we're left with an identity diagram above the pi by 4. Now, on the other side, we have two green nodes at the bottom, so we can do the same thing we did before, merge them by the spider law and then split them the other way, which leads us to that. And now we've got a red node here, which is a multiple of pi by 2, so we can't push that through the pi by 4. But what we can do is, if it has a minus sign, we can split it into a copy of pi by 2 and some multiple of red pi, and then we have a red pi back here, which we can push to the bottom. That's the pi by 4. And here, we've again done multiple steps in one, so pushing a pi through the pi by 4 would flip the phase, but we've then split the node again and pushed the remaining stuff through to the bottom. And so in this case, we're again left with a green pi by 4 in the middle, and some Clifford operators to the bottom of it. But now we've got this red pi by 2 stuff on top of the pi by 4, which we can't push further. So as you see, what we're left with in these two cases, at the top of the diagram, above the pi by 4, is either an identity, or a red pi by 2, if b is 0, or if b is 1, we have red pi by 2 and green pi by 2. So this is exactly an operator of the form that we previously called W. So we can rewrite these two diagrams into one as a W, a pi by 4, and then at the bottom we have a red operator, which is a multiple of pi, and then some green phase, which is going to be an arbitrary multiple of pi by 2, depending on what the Clifford operator was that we started with. So this is just the equation we just derived. If we take this red pi and the green phase and put them to the top of red pi by 2, we can now do the same thing that we tried to do before, so we try to push them through to the bottom. We're again going to distinguish cases depending on whether the green phase this time is a multiple of pi or not. In the first case, we can just, the two operators at the top are both multiples of pi, so we can just split them. And then we can push the red pi through the red pi by 2. We can push the green one through, which might flip the sign. But then we can again do the splitting and pushing the additional phase through to the bottom. So what we're left with is a red pi by 2, and then some green and red phases, which are multiples of pi at the bottom. And in the second case, we again have a green operator, which isn't a multiple of pi, but we can do the same trick that we used previously. So we're going to split it. No, sorry, first we move the red pi through just so that's done. And then we're going to split this operator into a green pi by 2 and then some green operator, which is a multiple of pi. So we can push that through, which again flips the sign, and then we fix that. So in this case, we're left with red pi by 2, again some operators that are just multiples of pi at the bottom, and this time potentially a green pi by 2 at the top. So so what we've done is we've had a Clifford operator sitting on top of the pi by 4, which pushed phase through, and then we've imagined that below the pi by 4 there was a red pi by 2, and we've tried to push as much as possible of the phases further through to the bottom. So if we try to combine these two results, here's just the general form of what we've just done. If we combine these two results, that gives us a number of rewriting identities, which we can use. So the red pi by 2 and the green pi by 4 together form a V. And so if we have a Clifford operator on top of one of these elements of form V, and then we can push things through to the bottom, and what we're left with is an operator of form W at the top, then some V, which may or may not be equal to the original one, and then some phase operators at the bottom, which are just copies of pi. Similarly, if we have an operator of form U at the bottom, which is a general Clifford operator with a green pi by 4 sitting on top of it, then we can do the same thing, and we'll again end up with some W at the top and some other U at the bottom. And a special case, lastly, of the first identity, if our original Clifford operator is just copies of red and green pi, then that just pushes through our V. And these are the identities we're going to use to rewrite arbitrary diagrams into this Clifford plus T normal form. So the way this proof works is basically because our generators for the single qubit Clifford plus T group are green pi by 4 and red pi by 2, in order to show that any diagram can be rewritten to normal form, all we need to do is show that if we have a diagram that is already in normal form, or is a pure Clifford operator, and we apply one of these two operators, then the resulting diagram can be rewritten to normal form, or it will be pure Clifford. So first, if we start with a Clifford operator and apply a red pi by 2, the result is still going to be Clifford, so that's trivial. If we start with a Clifford operator and compose that with a green pi by 4, then that's just the thing that we previously called U, which is a normal form diagram in its own right, because we don't have to have any copies of V, and the W that sits on the top of our normal form diagram can be the identity, so U in itself is a normal form diagram. So in this case, we're good. Now, the second case is where we have a diagram that's already in normal form, and we apply either one of our generators to the top of that diagram. We're just going to look at the topmost elements of the normal form diagram here. So at the very top, we're going to have some W, which is either an identity, a red pi by 2, or a red pi by 2 followed by green pi by 2. And below that, we're going to have some V, which is red pi by 2 and green pi by 4, or red pi by 2 and green 3 pi by 4. So if we put the red pi by 2 at the top of our diagram, then the red pi by 2 and the W together are just some Clifford operator. And then we have this identity which we derived previously, which says that we can push things through to the bottom, we're left with some other W at the top, and we have some copies of pi that come out at the bottom of the V operator. But the copies of pi can just be pushed through all the other V's that we might have further down, and they can be pushed all the way to the bottom of the diagram, and then the diagram is going to be in normal form again. And it's going to have the same number of copies of V as it had to start with, although they might look different to what they did before. In the second case, we have our V and our W, and we put a pi by 4 on top. Then there's two different cases. If W is the identity, the pi by 4 is going to combine with the V into some Clifford operator, because it'll add with the topmost node of the V, and then it'll be a multiple of pi by 2. So in that case, we have a Clifford operator, but that's just the case we've considered previously, just sort of with one fewer V's. So we know what to do in that case. We push phases through to the bottom, and then the diagram will end up being a normal form. In the second case, where W has some red pi by 2 inside it, the green pi by 4 is just going to combine with that into a new copy of V. So if we apply a green pi by 4 phase to our normal form diagram, the result is going to be either a normal form diagram which has one fewer copy of V, or one which has one more copy of V. But in either case, we can rewrite it to normal form. What we've neglected to do here so far is consider the cases where we don't have any V's to start with, we just have a U at the bottom, so the Clifford operator, one pi by 4 node, and then possibly some W at the top. But that's not a lot of cases. It's fairly easy to see that it works exactly the same as what we've done before, and we can always rewrite back to normal form. So this means that any single qubit Clifford plus T diagram can be rewritten into this normal form. So the normal form exists, which is a good start. We're now going to move on to show that the normal form is indeed unique, which is the second ingredient we need. And that proof has two parts. First, we show that no normal form diagram represents the identity. And then after that, we show that if we have two normal form diagrams that aren't identical, and we invert one of them and compose it with the other, the result is going to be a normal form diagram that has a non-trivial form. So because of this argument, it can't be the identity, and hence the two diagrams can't have been equal. So this is an argument about block sphere operators. Where any pure single qubit density operator can be written as some number times Pauli x plus some number times Pauli y plus some number times Pauli z. And then we can just take these numbers x, y, z and combine them into a vector. If we apply Clifford unitaries to our density operator, then the way this vector changes is just going to be by permutation of the elements and possibly by addition of minus signs. That's fairly easy. If we apply a t to our density operator, then what happens to this vector is it goes to the following form, so 1 over square root of 2 and a multiple of square root of 2 here, and some of them combine. And this means that if we apply a normal form operator to the state 0, then we're always going to get a vector of the following form, 1 over square root of 2 to some power, and then all the entries are going to be integers plus integers times square root of 2. And not all of these vectors will actually appear if we apply normal form diagrams to 0. And in fact, we can make parity arguments that show that none of the vectors that we will actually get from actual normal form diagrams can represent the state 0, and hence no normal form diagram is the identity because none of them take 0 back to itself. Next, we're going to look at inverting normal form diagrams and what happens then. We will show that we need the same number of pi/4 phase shifts in the inverse of the normal form diagram as we have in the original one. So if we, that kind of makes sense because pi/4 is a sort of resource when implementing operators, and it would be strange if the inverse of an operator required a different amount of resources to implement to the original operator. So if we invert our u, because that's just a Clifford operator followed by pi/4, it gives us pi/4 followed by some Clifford operator. And it's easy to show that if we inverted v, that's the same as taking the original v and having red pi/2s on top and bottom. So we can rewrite our inverted diagram in this form. We can then combine the pi/2s that sit in between different copies of v's into pi's, and the pi/2 and the green pi/4 at the top into a new element of form v. The pi's can all be pushed through to the bottom, and we can also push as much as possible of the Clifford operator through to the bottom, which means we end up with some new w on top. We might have a copy of green pi down here, and because we started with the red pi/2 down here, that will combine with the potential red pi phase into this. So now if we look at this bottom part of the diagram, this is Clifford, this is also Clifford, and then we have a v which has a Clifford operator and a green pi/4. So we can combine these 4 elements into a new thing that we call u. And then if we just relabel our v's, we see that basically the new diagram has the same structure as the original diagram, which is what we wanted to show. Therefore, if we have 2 normal form diagrams that aren't identical, we can now compose one diagram with the inverse of the other. And if we assume that the 2 diagrams are such that the topmost nodes differ, which we can assume because if the topmost nodes aren't different, we can just remove nodes from the top until the topmost nodes are different, and that won't change whether the 2 diagrams are equal or not. We can simply distinguish cases and see that the resulting diagram will never collapse back to just a straight line with no phase operators on it. And therefore, if we combine these 2 diagrams, they will never give us an identity, and hence they can't be equal. So that is the proof that our normal forms are unique, and that concludes the proof that the ZX calculus is complete for single qubit Clifford plus T operators. I'm now going to move on to a very quick overview of completeness for stabilizer diagrams. So stabilizer quantum mechanics basically means we can prepare qubits in the state 0, we can apply the single qubit Clifford operators, and because we now have multi-qubit diagrams, we can also have the controlled MOT operator, and we can measure in the computational basis. For the ZX calculus, that means we can now have nodes with arbitrary numbers of inputs and outputs, but our phases have to be multiples of pi/2. And we now have all the rules that Vladimir originally introduced, and yeah, the case that I had previously. The proof is mostly about graph states, which are defined as follows. So if we have a finite simple undirected graph, we can associate a quantum state with that, and the ZX calculus for this quantum state is particularly nice. For each node in the original graph, for example this one here, we have one green node with an output in our ZX diagram. These are basically the qubits. And for each edge in the original graph, we have an edge with a Hadamard on it in our ZX calculus diagram. This corresponds exactly to the way that graph states are normally defined in stabilizer quantum mechanics. The reason we're interested in graph states is because they have some very nice properties. As Van den Nest and others showed, any stabilizer state is local Clifford equivalent to some graph states. So just by using local Clifford operations, tensor products of single qubit operators, we can transform any stabilizer state into a graph state. Or we can prepare any stabilizer state by preparing the graph state and then applying local operations to it. Furthermore, 2 graph states are equivalent under local Clifford operations if and only if they are related by local complementations, which are a graphical way of describing the relationship between 2 graphs. They're a bit tricky, so I'm going to explain them by an example. If we have this line graph down here and we apply a local complementation about the vertex 3, the neighborhood of 3 are the vertices 2 and 4. And we're going to invert the subgraph generated by this neighborhood, which means we flip all the edges amongst the neighbors. In this case, that just means adding an edge between 2 and 4. Any edges that involve non-neighbor nodes, like the edge 2, 1, just remain unchanged. If we now apply another local complementation about vertex 2, 2 is adjacent to all the other vertices. So we we remove the edge 3, 4, and we add edges 1, 3, and 1, 4. And this is what a local complementation is. As Duncan and Padry showed, we can derive local complementations in the ZX calculus. We can use this to show then that Van der Nest's result hold in the ZX calculus. This is what I talked about in QPL 2 years ago. So any stabilized ZX calculus diagram can be rewritten into a graph state with local Clifford operators. So we have the graph state at the bottom here, and then we have arbitrary local operators, single qubit operators on each output. And given these graph states with local Clifford operators, there is an algorithm that allows us to decide whether two such diagrams are equal or not. If the diagrams are equal, it will rewrite them to be identical, which gives us the equality proof. And if they're not equal, it will stop at some point, in which case it's fairly easy to check whether they're identical or not. And if they're not, then we know that, yeah, we don't need to worry about this any further. So this paper is up on the archive. Right, that's it so far for my talk. So as Vladimir said, the ZX calculus is not complete overall, and we don't know how to complete it. But as I've shown just now, we can still find fragments of the ZX calculus which are complete. For example, line graphs where all phases are multiples of pi by 4, or arbitrary diagrams where phases are multiples of pi by 2. And an interesting next question is to see whether these results can be combined into a completeness proof for multi-qubit Clifford plus T operators. But yeah, it's not at all obvious whether that works or not. It might be difficult. And yeah, so the issue with the term approximate completeness has been brought up. So yeah, there is no notion in the ZX calculus of approximation. It would be interesting to see whether we can introduce something like that. But again, I'm not sure whether that's possible or even particularly sensible to do. Thank you.
Okay, is there any question? Yes,
Hi. So in Vladimir's talk, he said he wanted to have a rule exchanging the two versions of the already composition.
Mm-hmm.
So it seems to me that you could probably give such a rule for the Clifford plus T case using the result you have here. Is that correct?
So, I mean, in the Clifford plus T case, you don't have this general Euler decomposition rule because you're restricted to phases being multiples of pi by 4. And if you have some normal form operator, or some operator that involves pi by 4 phases, then if you try and flip things, they wouldn't necessarily be multiples of pi by 4, so they wouldn't be valid diagrams in the Clifford plus T ZX calculus. And hence we don't have those rules at all, and just avoid the problem.
Right. Okay.
Is there any other question? Yes?
Do you think the results can be combined to multi-qubit Clifford plus T operators?
Sorry, can you speak up a bit? There's noise outside.
Do you, the second bullet point on, can you conjecture yes or no?
I'm not sure. I think it might be no, but I've not looked into it quite enough yet to have a good idea. And even if it's currently like incomplete with the current rule set, it might be easier to complete it than it is for the general case, because yeah, we avoid all those issues of having arbitrary phases. So I think it's still worth investigating.
If there are no more questions, let's thank Miriam again. Move to the fourth and last talk of the morning, which is by Linde Wester, who is now. And the title of the talk will be Mixed quantum states in higher categories.